Hello. This video gives you a short introduction to our tutorial paper about visual place recognition that is published in the IEEE Robotics and Automation Magazine. The paper is open access so that you can download and read it for free. We also provide an associated GitHub repository, which allows you to test or build your own visual place recognition pipeline. I am Stefan Schubert from the Chemnitz University of Technology, and this is joint work with Per Neubert from the University of Koblenz, Sourav Garg from the University of Adelaide, and Michael Milford and Tobias Fischer from the Queensland University of Technology. For all newcomers to the field, let's start with a brief definition of visual place recognition. In a nutshell, visual place recognition, or VPR for short, is the ability to recognize known or previously seen places in the world based solely on images, potentially despite severe appearance changes or large viewpoint changes. Typical use cases are visual localization, loop closure detection for simultaneous localization and mapping, and the identification of shared places for multi-session or multi-robot mapping. Visual place recognition is a research field with significant and continuous growth over the years, as can be seen by the number of publications per year with visual place recognition in the title. Therefore, a number of survey and benchmarking articles have already discussed challenges, open questions, and achievements in the field of VPR. The present work is the first tutorial article on VPR. It unifies the terminology of VPR and complements prior research. Our tutorial paper is intended for both newcomers to the field and researchers who are acquainted with the visual place recognition problems. For newcomers, it provides a systematic introduction to the field, covering topics such as the formulation of the VPR problem, a generic algorithmic pipeline, an evaluation methodology for VPR approaches, and the major challenges for VPR and how they may be addressed. As a contribution to researchers acquainted with the VPR problem, it examines the intricacies of different VPR problem types regarding input, data processing, and output. The tutorial also discusses subtleties behind the evaluation of VPR algorithms. In the following, some of these topics are shortly introduced. All details can be found in our paper. Our tutorial starts with the basics of VPR. Typical VPR approaches are based on an image database of known places and on one or more query images. All images could be recorded with a camera, mounted on a variety of platforms, such as a car or an uncrewed aerial vehicle, or with mobile devices, such as an augmented reality headset or your cell phone. Given both image sets, each image pair between the query set and the database has to be compared to find same places. For the pairwise image comparison, our tutorial presents a generic pipeline that is the basis for many VPR pipelines in the literature. Inputs to the pipeline are the database and the query set. For each image in both sets, an image descriptor is computed. The similarity between image pairs can then be measured with the descriptor similarity using either simple Euclidean or cosine distance or more complex algorithmic approaches. All pairwise similarities are accumulated in a similarity matrix S, and the similarity matrix is finally used for matching decisions to identify same places. The details of the individual steps and elements of this generic pipeline are explained in our paper. For example, we discussed the relation between the appearance of the similarity matrix S and the camera trajectories. For the evaluation of the VPR pipeline, important details about data sets, the ground truth, and different metrics are presented. For example, the tutorial covers the intricacies behind the evaluation of VPR algorithms and defines precision and recall for the evaluation of a VPR system that must find either a single or all matching database images per query image. Regarding the input, the data processing, and the output of a VPR pipeline, our tutorial discusses VPR problem categories with their intricacies and corresponding use cases. The input to a VPR pipeline can be either two separate input sets, one for the database and one for the query set, or a single set that is compared to itself. Here we distinguish between single-session VPR and multi-session VPR. Regarding the data processing, a VPR pipeline processes all images either individually, one after the other, or in a single batch. Accordingly, VPR approaches can be classified as online VPR or batch VPR. The output of a VPR pipeline can be a single image from the database that shows the same place as a query image, or all database images that show the same place as a query image. These categories are referred to as single best match VPR and multi-match VPR. Different input and data processing categories lead to different use cases, as shown on the slide. For example, Online SLAM runs in a single session and compares a current query image to previous query images online. Accordingly, single session online VPR is used for Online SLAM. The output category rather determines which algorithms can be used for a specific use case. The final section in our paper goes beyond the generic pipeline and lists 4 major challenges faced by researchers in the field of VPR. The first challenge is scalability, or how to scale up a VPR system to handle large numbers of images. The second challenge is appearance change, for example, due to dynamic objects, time of day, weather, or seasons. The third challenge is viewpoint variation when revisiting places. And the fourth challenge is performance improvement, or how to perform better. How these challenges may be addressed is discussed in our paper with corresponding related literature. In conclusion, visual place recognition is an active research field with many different aspects. To learn more about visual place recognition, take a look at our tutorial paper published in the IEEE Robotics and Automation Magazine, which is open access. Associated code allows you to easily experiment with the generic visual place recognition pipeline with several descriptors, data sets, and performance metrics.